Hi everyone. Today we are going to solve a problem on bolted connections. I hope you all have all gone through the videos and the notes that were given in the previous lectures. So here is a problem of a lap joint. That means there are two plates connected and they are overlapping each other, and they're connected by means of 6 bolts as seen in the diagram. Okay, so this is 1, 2, 3, 4, 5, and there are 6 bolts. You are given that the bolts are M20 bolts. The grade of the bolt is 4.6 and Fe410 plates are used. So let us start solving this problem. So for M20 grade of bolts with 4.6 M20 bolts of 4.6 grade, the ultimate strength this was provided in the notes. FUB is 400 megapascals. Okay, so the partial safety factor this we have seen in the tension members. Gamma MB is 1.25 and the diameter of the bolt is given to us as 20 mm. M20 meaning the dia of the bolt is 20. So the dia of the hole, okay, D0 will be 20 plus 2, which is 22 mm. The ultimate stress of the plates Fu is given as 410 and the partial safety factor for plates gamma M1 equals to 1.25. Now let us calculate the strength of plates. Here we are given two plates of the same thickness, but when we are designing the strength, or we are finding out the strength of the plates, we should consider the thickness of the thinner plate. Thickness of thinner plate is 20 mm. Width of the plate is 180 mm as seen in the diagram. There is no staggering. Now we see that the bolts are in one line, so there is no staggering. So PSI is 0. The number of bolts in the weakest section, okay, so in each row there are 3, so the number of bolts in each section is 3. To find out the net area, at the weakest section, or we call it the critical section, AN will be B, that is the width, the number of the diameter of the hole, plus PSI. Okay, so since psi upon the 4g. Psi value is 0, so this will be 0 into T. Okay, this comes up to 2280 mm square. So this term here is psi square upon 4gi, and since psi is 0, the entire term is 0. Next we need to calculate the design strength of plates in the joint. Which is denoted by T suffix Dn. Substituting all the values in this equation, we get 673.056 kilonewton, which means that the plates can take a force of 673.056 kilonewton. Now we have to find out the strength of bolts. Total number of bolts is 6. When we are designing bolts, first let us design strength in shear. Let's find out the design strength in shear. Now in this diagram here, in the cross section, it is not clear where the shank portion is and where the threaded portion begins. Okay, so all we can see is some threaded portion here. Okay, we can see only a threaded portion in that part. So let us assume that the shear plane is in the threaded portion. We need to find out Nn and Ns. We know that Nn is the number of shear planes which are intercepting the threaded portion. So since we are assuming that the shear plane is in the threaded portion, okay, we see here there is only one shear plane. There is just one shear plane here. This is the one. Okay, so between two plates there is one shear plane, and we are assuming that it is in the threaded portion. So this will be 1 and Ns will be 0. So total number, this is 1 per bolt, right? We have 6 bolts, so total number of Nn will be 1 into 6, which is 6, and Ns will be 0. Now to calculate A and B, we know that we have to take 0.78 and the area of the bolt. This works out to be 245 mm square. There are no reduction factors given, okay? So beta Lj, no details are given in the problem. So the grip length, the length of joint, the packing reduction is taken as 1. To find out the nominal shear strength is given by V suffix NSB upon root 3 NN ANB plus NS into ASB. So this term will become 0 since NS is 0, and substituting all the values here, you will get 339.482 kilonewton. Now what happens if you take NN as 0 and NS as 1? This value here changes. Okay, so it entirely depends on the assumption that you have made initially. Therefore, the design strength in shear VDSB is given by the nominal shear strength upon the partial safety factor of the bolt, 482 upon 1.25. This works out to be 271.586 kilonewton. So we have found out only the design strength in shear. The remaining part of the problem I will solve in the consequent videos. Thank you.